it, and at the same time, can all my active data set be cached in memory? Will that be a good approach by just increasing the memory in such a way that all the active data set could be cached in memory? And do I have a lot of sequence scans versus index scans? So all of this data can be analyzed, right? And it may be helpful in understanding the behavior of your database. And at the same time, you may have several unused indexes, which could even be writing, which could be involved in writing a lot of, performing a lot of write IOPS onto the database. And at the same time, bloated tables, and you may identify bloated tables and vacuum them to improve performance. And you may partition bigger tables so that, the amount of data that's fetched from the disk could be lesser, and at the same time moving tables between table spaces so that you could distribute the IOPS across multiple disks, right? Maybe moving the hot data to different table spaces that are on flash disk could be, right? So these are some of the tuning techniques that you follow, which are very in general. But I would definitely want to go ahead and start talking about some of the mistaken parameters in Postgres. And once we are done with the mistaken parameters, I would want to discuss about the ignored parameters in Postgres, right? So when we talk about the mistaken parameters, what I'm going to talk about is pick up 12 Postgres parameters and explain what they mean, and also explain you how sometimes we mistakenly set different values to it, but how they are supposedly to be set. So the first parameter that comes to our mind when we are talking about tuning Postgres is shared buffers. So I would want to start there, right? So what is this parameter? It's basically the memory, right, for Postgres. So that's the database memory area, and all the pages that are being dirtied or requested by the client are fetched to this shared buffers, and then it uses the LRU algorithm, the least recently used algorithm, to flush the pages away from the shared buffers. So what we do is we follow a magic number, like 25% of the total RAM, or some time back, like few years ago at conferences, I used to see people talking about allocate 8 gigs to shared buffers. That was a magic number, right? I don't know how many of you have heard about it, but 8 gigs used to be the magic number. 25% of total RAM used to be a magic number too. But it's not the same all the time. 90% of the total RAM could also get you better performance, right? And what you need to understand is PostgreSQL does not do direct I/O. So what is direct I/O? Consider Oracle and MySQL like databases. Let's say you run a select query on a table, and that select query need to basically fetch from records which are there in the pages that are on the disk. Now they are fetched from the disk to the memory area of the database, which could be database buffer cache in Oracle, or the InnoDB buffer pool in MySQL. Likewise, in Postgres, it could be shared buffers. So the pages from the disk need to be fetched to the memory, right? But in Postgres, it's not directly fetched from OS to shared buffers. When the page that it needs is not found in shared buffers, Postgres would go ahead and request the operating system. And OS would fetch that page and get it to the OS cache, and from there it will be copied to the shared buffers, right? So this way, you may be actually double caching, right? So that's why we keep hearing about give more priority to OS cache sometimes. But it's not all the time. I mean, when you can put all your active data set in memory, and at the same time you do not have huge amount of sorts happening, and your Workmen can be set to too low, right? You could basically go ahead and try to understand your system better in a way that you could understand whether you could set more, you could give more RAM to shared buffers or less RAM to shared buffers, right? And PG buffer cache is one of the beautiful extensions available in Postgres to understand what's in your shared buffers. So you could see how much portion of a table is stored in, is currently in the shared buffer. So you could snapshot that to understand your hot or the active data set, right? So shared buffers need not be this 25% or the 8 GB magic number all the time. Try to use PG buffer cache extension and see what's in the shared buffers. At the same time, use VMTouch or some other OS tools to understand what are those files that are frequently cached in memory. And then you could understand how much amount of shared buffers can actually be allocated so that every request is served just from shared buffers. Or you may reduce the shared buffers and give more preference to the OS cache. Workmen. Again, this is the where basically workmem, if I remember correctly, 4 megabytes is the default workmem value, right? And when you just install Postgres, the value set to workmem would be 4 megabytes. What does it do? It means that amount of memory will be allocated for each sort operation, right? And if in case your query is performing multiple sort operations, n times this workmem amount of memory is allocated to that. So basically, you may want to increase it so that you could avoid writing to temp files which are on the disk, because writing to memory is always more faster. Anything that's happening in RAM is more faster than on the disk, right? However, in some of the analytics as well as some of the reporting queries that you run, or some other type of different workloads, you may need to have more workmem. I've seen environments where they set 256 megabytes of workmem, or 128 MB, or even 1 gig. But when you do that, you need to remember, if in case you have, let's say, 1,000 max connections, which is not the right number, maybe. Let's say you have 100 or 200 max connections set. I'm sorry. And you have, that means so many concurrent connections can run at a point of time. And you also have workmem set to 128 megabytes. So 128 times 100, right? And let's say each query is doing more than one sort operation, it could be times n. So much RAM is just dedicated to perform sorting. And you could really get into out-of-memory situations, right? So it's not always that you could just increase workmem to avoid writing to temp. So you could query views like pgstat database to see how much of temp is being written, right? How much of temp generation is happening just by snapshotting pgstat database view. But just by looking at that, we cannot just go ahead and globally increase the workmem. If you have specific SQLs or the queries or analytic reporting queries which need more workmem, use session level workmem instead. From your application, use session level workmem, which is just like set workmem to 1 GB or 512 MB. And that would only be valid for that session. Do not increase the workmem globally when you need to increase it to bigger numbers. And when you do that, you could get into these errors. Effective cache size. So this is only used for estimation purposes. Most of the time, people mistakenly, they assume that this is reserved for cache or from the cache, right? But that's not what it is. So what it is used for is the planner, the optimizer, Postgres optimizer, would basically see how much of effective cache size is available. So it then assumes that so much of RAM is available for caching indexes, right? Based on that, it gives priority to index scans over sequence scans. And if you set it to too low, then it would prefer a sequence scan. So usually, like in most of the environments, you see people setting it to 70% or more when you have faster disks, and indexes can always be cached, right? So setting it to 70% or 90% doesn't mean that it reserves any memory. It basically is only used for estimation purposes, nothing else. AutoVacuum. right? Many of us, or maybe not from here, I mean in this room, but most of the users sometimes just go ahead and say, I would like to turn AutoVacuum, sorry, I would like to turn, sorry, can I get some water? Yeah, I would like to turn AutoVacuum to off. And when you do that, you need to understand that there are three activities being performed by AutoVacuum. And that is freezing the exides of table, cleaning dead tuples, and at the same time, updating statistics of table. So these three activities, you need to go ahead and write your own manual vacuum logic, which is very, very difficult to hack. So, thanks. I'm shouting after a very long time. Yeah. OK. So always make sure that you're never turning it off. Because if you're turning it off, then you need to handle one of the important aspects, which is freezing of exides. Because you could get into a transaction ID wraparound problem. How many of you really understand the transaction ID wraparound problem? OK. OK. So, but we can definitely talk about it after this session. You could meet me if in case you would like to know that. But to avoid that, you need to have AutoVacuum running, right? Yeah. And so never turn this to off if somebody says that, because there can be three important activities that can be affected. Track counts. So we discussed about the three important activities done by the AutoVacuum. And those activities will only be performed by the statistics collected when track counts is set to on. If track counts is set to off, then AutoVacuum does not know, what happened earlier, like how many inserts, updates, deletes have happened. Those statistics are not captured. And now AutoVacuum does not know what to do except for freezing, right? So never set this to off, because the tracking of statistics will not work. And the important and the most important parameters now related to AutoVacuum, vacuum scale factor and vacuum threshold. I'm going to talk about some of the algorithms, and it'll be very interesting starting from here, right? So we'll also talk about AutoVacuum, analyze scale factor, and analyze threshold. So what is AutoVacuum vacuum? We discussed about AutoVacuum. Always, it should be on, and it has got several activities that it should do. So one of the important aspects is it cleaning up the dead tuples. What are dead tuples, right? In Oracle and MySQL, when a delete happens or an update happens, right? An update is also an insert and a delete. So when tuples are deleted, those deleted tuples are stored in a separate storage for undo, for rollback, right? Or for consistency. But in Postgres, they are stored in its own table. And when it's stored in its own table, it's stored as multiple versions, right? Through the transaction ID that actually deleted it. So what we are trying to say is the undo is also stored in its own table, but not a separate storage, right? And now in order to clean up those older versions, we need this AutoVacuum process. And when AutoVacuum is set to on, based on the statistics collected, because track counts is set to on, right? Based on those statistics, an AutoVacuum vacuum, which is to clean up those dead tuples, nothing but the older version deleted records, right? To clean up will start on the tables. And those start when sum of updates plus deletes is equal to scale factor times total number of tuples plus vacuum threshold, right? So when this formula is satisfied, right, based on the statistics collected due to track counts being set to on, right, then our AutoVacuum vacuum runs on a table. And now that cleans up the dead tuples. And if possible, also freezes the tuples XID, which is something totally different. We can talk about that later. So scale factor is the fraction of table records that will be added to the formula. So 0.2 means 20% of the table records. 0.2 means 20%. And vacuum threshold is the minimum number of obsolete records. So the default of vacuum threshold is 50, and the default of scale factor is 0.2. Now, to understand all of this, just understand this formula, right? So if AutoVacuum vacuum scale factor is set to 0.2, and if you have total number of tuples, nothing but records or rows in a table equal to 1,000, and vacuum threshold equal to 50, that means 1,000 into 0.2 plus 50, which is 250. So for every 250 updates plus deletes, we see the table as a candidate for AutoVacuum vacuum, right? So based on this formula, when we have 1,000 tuples. And how many such AutoVacuums can run at a point of time? It depends on the AutoVacuum max workers. We'll talk about that process. And each worker process within each database, every AutoVacuum nap time seconds is started. That's usually set to 1 minute, right? So if there are n databases, a worker is launched every AutoVacuum nap time by n seconds, right? So there will be a cycle of AutoVacuums running all the time in your database. So these are global settings, right? Similarly, AutoVacuum analyze. What does analyze do? Analyze updates the statistics so that the optimizer could use them while preparing execution plans. So here we are talking about statistics through analyze, and sometime back we talked about statistics through track counts. And what track counts is actually doing is the stats collector process, the background process, is basically trying to understand or capture how many inserts, updates, and deletes are happening on the database. And that data will be used by AutoVacuum. But these statistics that are collected through analyze will be used by the optimizer to prepare execution plans. So similar to AutoVacuum vacuum scale factor, you also have AutoVacuum analyze scale factor, which is equal to the fraction of table records. So 0.1 is the default. So it means 10% of table records. It should be AutoVacuum analyze threshold. It's a mistake, spelling mistake. So it's a number of, so just look at this formula again. The analyze scale factor is set to 0.1. Total number of tuples, 1,000. Analyze threshold is 50, which means for every 150 inserts plus updates plus deletes, you see an AutoVacuum analyze. Again, a spelling mistake. So the AutoVacuum launcher process basically spawns the worker process that runs either the vacuum or the analyze when these formulas are reached. Okay? So far you just need to understand just basic things about AutoVacuum, vacuum, or analyze. Vacuum cleans up the dead tuples, and analyze updates the statistics. And AutoVacuum is a background process that takes care of these based on these formulas. Now, how to set it correctly? Global parameters may not be appropriate all the time. Why? Because it's regardless of the size of the table. Consider two tables with 10 records and 1,000,000 records, right? Through those formulas, the frequency at which a vacuum or an analyze runs automatically could be greater for the table with just 10 records. Isn't that right? Yeah? So instead, use table level AutoVacuum settings. Okay? So see what are those tables that are frequently vacuumed due to this reason, right? And see if you can set table level AutoVacuum. And most of the times I see people still taking care of vacuum logic manually. Yes, by keeping the AutoVacuum set to on, it's okay to go ahead and look for those tables that are missing vacuum due to that condition, and run a nightly or a weekly vacuum. And vacuum is online operation. It does not lock any of the activity, right? And as I was discussing earlier, there cannot be more than AutoVacuum max workers number of AutoVacuum processes. And this AutoVacuum process includes vacuum and analyze together, right? So there cannot be 3. There cannot be anything more than 3. That's a default number. We could always change it. We could always increase that number as well. But we'll talk about that. In order to talk about that, we need to talk about AutoVacuum I/O, right? So an AutoVacuum reads 8 KB pages of a table from the disk, right? And it then, so what AutoVacuum does basically, it fetches the pages from the disk and then looks for the pages, nothing but the blocks, right, that have the dead tuples, and cleans those dead tuples up so that the future inserts could reuse that space. That's clear, right? So an AutoVacuum fetches a page of a table from the disk to memory and deletes the dead tuple and updates the free space map so that that space can be reused by the future insert, right? And so considering the default block size as 8 kilobyte, it involves both read and also write I/O, right? When it's cleaning up the dead tuples, it's a write I/O. When it's fetching the block or the page from the disk, it's a read I/O. There are 4 or 5 parameters that you need to consider. Again, AutoVacuum vacuum cost limit. The total cost limit the AutoVacuum could reach. So it's basically combined by all the AutoVacuum jobs. So what is the total amount of cost that can be reached by all the AutoVacuum processes together? And if it goes beyond that cost, then it needs to pause itself and proceed further after a pause. And that pause is the AutoVacuum vacuum cost delay. We'll see how this cost is calculated a little later. So it waits for so much of amount of time when this cost is reached. Vacuum cost page hit. This parameter, the default value is set to 1. What this means is, what is the cost of reading a page or a block that is already in shared buffers? And vacuum cost page miss is the cost of fetching a page that is not in shared buffers from the disk. And vacuum cost page dirty is the cost of writing to each page when there are dead tuples in it. So cost of reading for a page from memory is cost page hit. Cost page hit miss is the cost of fetching a page that is not in shared buffers, and page dirty is the cost of writing to each page when dirty buffers are there in it, or dead tuples are there in it. So let's look at the defaults. AutoVacuum vacuum cost limit is set to -1 by default. So what it means is it defaults to vacuum cost limit now. And what is vacuum cost limit? It is set to 200. Okay? And AutoVacuum vacuum cost delay is set to 20 milliseconds. So when that 200 cost is reached, the AutoVacuum should pause for 20 milliseconds. Cost of fetching a page from shared buffers, cost page hit is 1. Cost page miss, when it's not there in shared buffers fetching a page from the disk, that is 10. Cost page dirty, to clear the dead tuples, that means a write to a page, is 20. So let's imagine what can happen in 1 second. 1 second is equal to 1,000 milliseconds, right? In a best case scenario, considering the read latency is 0 milliseconds, AutoVacuum can wake up and go for sleep 50 times. That means 1,000 milliseconds by 20 milliseconds is 50, right? So let's consider AutoVacuum started, it reached the cost, it sleeps for 20 milliseconds, again starts, reaches the cost, again 20 milliseconds of sleep. So considering how many times it could sleep, right? It could sleep 50 times in 1 second, the most. And 1 second is equal to 50 into AutoVacuum vacuum cost delay. Now, read IO limitation. If all the pages with dead tuples are found in shared buffers, in every wake up, 200 pages can be read, because cost of reading a page from shared buffers is 1, right? So it's nothing but 200 into 1, or 200 divided by 1, right? So in 1 second, 50 times 200 by vacuum page cost page hit into 8 kilobytes. So in 1 second, with the default parameters, 78.13 megabytes can be read by all the AutoVacuum processes based on the default settings. And if pages are not in shared buffers, then with the formula, it can read up to 7.81 megabytes per second from the disk. And it can write up to 3.9 megabytes per second to the disk, or it can to the pages, basically, right? So these are the read IO and the write IO limitations with the default parameters. Now consider increasing the AutoVacuum max workers. What happens? You increase that from 3 to 6. These limits are shared by all those worker processes. Is that any benefit? No, right? So just increasing the worker processes is not a benefit all the time. You need to consider even these parameters that are basically talking about the cost limits. So that's what our next slide is all about. So it is a number of AutoVacuum workers that could run concurrently, defaults to 3. Check for the number of databases. Just increasing this would not work, because the cost limit is shared across all the vacuums. So you must go ahead and increase. For example, increasing vacuum cost limit to 2000 means 781 megabytes of reads per second from the memory, and 71 megabytes of reads from the disk, and 39 megabytes of writes per second, right? So consider your disk and check how much IOPS it can handle, right? And then based on all the other things that you applied, like adding the most fastest disk, like a flash disk, or could be, like you scattered all your tables to multiple disks, and then check how much writes and reads it could handle. And based on that, tune the cost limit and increase the max workers proportionally, right? So that is what you need to do in order to go ahead and play with the AutoVacuum settings to finish your AutoVacuum more faster, yes?
These defaults are more for spinning disks than SSD in terms of the proportion between it and dirty?
So these defaults are basically the numbers that we are telling Postgres, this is the cost. So that's why we could go ahead and play with those defaults and change it when we know about the disk. Yes. So these defaults are done pretty long back, considering the disk, the older hard disks, right? These defaults work for them. But nowadays, SSDs are, quite, the faster disks are quite more often. You could use them. And the last mistaken parameter before we go into the ignored parameters, maintenance workmem. So this is the amount of memory, nothing but from the RAM, used by maintenance operations such as create index and alter table add foreign key, like maintenance tasks. So in order to perform a faster database restore, you may go ahead and increase your maintenance workmem so that the create index at least works more faster, right? So it'll be better performant. It'll be better performant when you set this to a higher value during a database restore. How to set it correctly? If your AutoVacuum workmem is left at -1, which is the default, right? Even your AutoVacuums could use maintenance workmem amount of RAM, right? If you have enough faster disk and it can, do all its job nicely, it could take more RAM. So careful with that when you're setting it, and at the same time, check this formula as well, right? Number of concurrent maintenance operations during peak times maintenance workmem should be very much less than total RAM minus shared buffers plus workmem times max concurrent connections times n. And that n, it looks like a totally difficult formula to understand, but when you basically look at the slides and try to relate it, maybe, yeah. But that n is nothing but the number of sort operations that are happening per each query, because sometimes each SQL may have like more sort operations than one, right? So that n can be substituted by that. So it's just a formula that anyone could come up with. I mean, I know people can change many things in it. So ignored parameters. Let's look at very few ignored parameters. Random page cost, right? So this is a frequently ignored setting whenever we kind of perform architectural health checks and or look at the customer environments. We do see frequently this setting being ignored. It is the cost of non-sequentially fetched disk page, because indexes are considered to be random scan, right? The default is set to 4. So as this cost is set to 4 and sequence page cost is set to 1, right? An optimizer could basically prefer a sequence scan more. So if you go ahead and query pgstat user tables and look at the number of sequence scans of a table, compare it with the index scan, sometimes a table that has got an index could be performing better when that index is scanned, but still optimizer preferring the sequence scan, right? And that could be due to these settings, because you're telling that the random page cost is more. And when you do that, when the planner prepares the execution plan, because it's a cost-based optimizer, the cost could be higher considering random page cost equal to 4. But when you have a faster disk, nowadays SSDs are default, right? You may be able to go ahead and set random page cost right equal to the sequence page cost. In that case, the optimizer would now know, okay, I could rather go ahead and prefer an index scan. Wall compression, right? This is one more important parameter, I think starting from Postgres 9.5, if I remember correctly. So this is, again, one more frequently ignored parameter. Default is off, right? What it does is, we need to be very careful. Every time a checkpoint happens, right? Every time a checkpoint happens, right after the checkpoint, the first change to a page or a database block will always make a full page write to a wall, right? And the subsequent changes only captures the wall records anyway. So those full page images that are written to wall are compressed, right? And basically, that would only happen when you turn it to on. It of course, is at an expense of the CPU, but it is helpful when you have too many transaction walls or logs being generated in Postgres. So for example, in one of our workload where we generated 3.3 terabytes of walls, it decreased to 1.9 terabyte when we set it to on, right? So it could be improving the performance when you are able to take a hit on the CPU, right? I mean, which is not huge, but even replication, it basically has to uncompress that and apply. So considering all those, still wall compression, turning it to on is most of the times a win. Checkpoint timeout, very, very important parameter that I would like to explain. Some time back, we talked about the full page being written to a wall after a checkpoint for its first change, right? So considering the default checkpoint of 5 minutes, what it means that is every 5 minutes, the checkpointer process would go ahead and perform a lot of writes, and but that frequent checkpointing could degrade the performance due to more writes that can be possible, right? When compared to the checkpoint timeout value being set to 15 minutes or more, right? I mean, these 50 minutes or 30 minutes could be some magic numbers just to show you, but you may be able to increase the checkpoint timeout value to a bigger number, right? Because that's how you're reducing the number of full page writes to the disk, to the walls, right? And so the amount of work that needs to be performed even by the checkpointer at a later point of time is pretty less. So when you kind of configure or leave it at the default, every 5 minutes the checkpoint needs to start writing, and that could cause performance impact. So, but when you increase the checkpoint timeout to a bigger number like 15 minutes or 30 or 1 hour, the crash recovery time, the after crash recovery time could be more, right? Because it has got a lot of work to do now. Instead of doing the work, applying all the transactions since the past 5 minutes, now it has to start looking at everything since the past 15 minutes or 1 hour. That's more faster. I mean, you could just test that in your environment, or even before shutdown, because there is a shutdown checkpoint that's issued, right? You could perform a manual checkpoint and issue a shutdown. I mean, you could log all the checkpoint activities and see how frequently checkpoints are being performed, right? And the last ignored parameter would be checkpoint completion target. The default is set to 0.5, right? So it is basically helpful for spreading our checkpoints. So consider checkpoint completion target as 0.5 and checkpoint timeout set to 30 minutes. So 0.5 into 30 minutes, which is 15 minutes. So your checkpoint activity can be spread across 15 minutes. Instead, you could even set it to 0.8 or 0.9 and spread it across 27 minutes. So that way, your writes are evenly distributed, whatever is being performed by checkpoint, and it has got much more relaxed time to do. It has got a bigger window to apply the checkpoint, right? So this could be a helpful parameter too. And the last and the final one, max wall size. It's not just the checkpoint timeout that triggers a checkpoint, right? Even if in case max wall size amount of walls are reached, which defaults to 1 GB, a checkpoint could still be triggered. So if you just go ahead and increase your checkpoint timeout to 1 hour or 30 minutes and still see checkpoints happening every 5 minutes or 10 minutes, look at the max wall size. You might have to increase that to 5 gigs or 10 gigs because so much amount of walls could be generated in your database. So checkpoint is one of the important activity that you need to tune in your production database because it looks simple, but it has got a lot of benefit when you really tune it right. So make sure that you have enough disk space and check the checkpoint timeout and log the checkpoint activity, and accordingly even look at the amount of walls being generated. You have some functions available in Postgres where you could do pgwall diff and LSN diff and see how, what is the beginning wall and the ending wall between a 1 hour window. You know, you could basically use some functions to understand how much of wall is being generated, right, in an hour. So it would definitely be helpful if you consider this parameter as well. So one of the use case where we really performed the benchmark was using Sysbench. It's a multi-threaded benchmark tool where it's a 335 gigs database size on a Intel Xeon CPU and 56 threads, 256 gigs of RAM, almost everything in the memory, right? Active data set can quickly sit in the memory, and you have a nice SSD storage on an Ubuntu 16 OLTP type works load. So just to speed up the data load, as I am perfectly aware, because I told you earlier, like when you're turning off AutoVacuum, you need to rewrite or hack the algorithm, or you need to know, I mean, if it can really cause a problem. But in my case, I really do not know that it's not causing any problem. I disabled it. But right after that, I did perform a vacuum DB in parallel threads. And I was also keeping a track of the transaction IDs being generated. So I was able to do that. So just to speed up the load, I've set these parameters. And then I've gone ahead and run the Sysbench TPCC test, right? And so just the default untuned parameters was resulting into 1978 TPS. And tuned parameters, the tuning settings that we discussed just now, it resulted like 5,736 TPS. It was on a Postgres 11, not on 12, which is still in beta or being released. And crash unsafe, like disabling synchronous commit, fsync, which people should not do, right? It's not recommended. It got me more TPS, right? So yeah, that could be helpful when you're doing a data load and you want to, you understand that you monitor your transaction IDs, it's okay. But so, yeah, just a better representation of the numbers through diagrams or the bar diagram. So these are all those tune parameters, basically most of the things that we discussed today, right, that helped reaching those numbers. But though I wouldn't say these are just the only parameters, but these are some of the parameters that you could consider getting a good benefit immediately if they are not tuned right. Exactly. So in the beginning slide, I was talking about shared buffers, right, where we kind of consider the magic numbers like 25% of RAM or 8 gigs, but that may not be in all the cases when your entire database or the active data set can sit in memory, right? You could definitely increase that, right? I mean, there was one more beautiful blog, or the blog as well as a presentation done by Robert Haas explaining how he got much more better performance when he went up to like 90% of RAM for the shared buffer. So yeah, so it all depends on your workload and server resources that you have and the database size and the active data set. So for my environment, I was able to understand that the hot data, the active data set, can all fit in memory, and it's almost around 190 gigs. So I set all that to shared buffers instead of copying that from OS to memory. So that's what even Amazon Aurora does. Like they allocate 75% of RAM to shared buffers. Yeah.
I'm just curious in this example why you ended up setting your global AutoVacuum vacuum scale factor higher rather than lower to make AutoVacuum more aggressive.
Okay.
It looks like it would be less aggressive.
So here, the AutoVacuum vacuum scale factor is set to 0.4, but I had my manual vacuums running in the backend, like through table level vacuum settings. So that is what I've done. So there were 15 or 18 tables in the backend that I've created, and I've got proportionally like a separate cron script that is performing a different vacuum logic than what it is with Postgres, because manual vacuuming is more aggressive, and at the same time, the AutoVacuum vacuum, the way the database get into the list and Postgres performs a vacuum on it. For my example, because I was talking about how a table with lesser records can get more priority for vacuuming, right? So that's why I had to write a manual vacuum logic for it, and I increased the global settings. So sometimes you could even put the thresholds to 1 billion and 2 billion or 10 billion records so that the AutoVacuum vacuum will never start on that table, and I can handle that manually, right? So these are some settings that we can play with, but carefully, which is not recommended. Yeah, this is just for this test because I've done some of the magic in the back end. Yeah. Any other questions? Which is before that, I would like to thank Percona, who has sponsored me for this conference, and PostgresOpen Florida for giving me the opportunity to present here, right? We also have Percona Live 2019 taking place in Amsterdam, Netherlands. That will be definitely an interesting conference, which is for not just Postgres, MySQL, MongoDB, almost all the open source databases. And you could use my discount code to get a 20% discount and have fun in Amsterdam. Questions? Yeah. Are we on time? Yeah. I think yes. 2 minutes ahead. Yeah, so in case somebody would like to know about transaction ID wraparound and how that works, feel free to reach out to me. Or you could just search for MVCC internals Avinash. And there's one of the talks that I've given in PGConf India. And that was the talks that was clearly talking about transaction ID wraparound and explaining most of the internals. That's a 15-minute talk. You could see the slides and everything there. Yeah. Thank you.